Hello everyone, welcome back. This is lecture 11. In the last lecture, we talked about geometric series and some convergence tests. Today we're going to define P-series and then introduce more convergence tests that can be used to determine if a series converges or not. All right, so first thing is P-series. What is a P-series? Definition of P-series. Let P be a positive integer Okay, so when we're talking about P-series, we automatically assume that P is a positive, well, I don't mean a positive integer, I mean a positive number or constant. And an infinite series of the form and from 1 to infinity, 1 over n to the p, which is, if you write out the entire sum, it's 1 over n plus 1 over n squared plus, it's 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p, so on and so forth. This is called a P-series. And if p equals 1, p equals 1 gives us this series, 1 over n to the 1, which is 1 over 1 plus 1 over 2 plus 1 over 3 plus dot dot dot. So this special P-series with p equals 1 is called the harmonic series. Okay, so harmonic series is a special type of P-series with p equals 1. Let me give you a couple examples. The sum of 1 over n cubed. This, if you go back to the formula of P-series, then this is obviously a P-series with p equals 1. P equals 3. And then the sum of 1 over square root of n. Well, this, since it equals square root of n equals n to the 1 over 2, then this is a P-series with p equals 1 over 2. The last example, and from 1 to infinity of 1 over 3 to the n. Now notice that here n is on the exponent, not the base of the exponential. So this is not a P-series, right? This is not a p-series, but a geometric series. We talked about geometric series in the last lecture. A geometric series is essentially a series where each term is a constant multiple of the previous. So in this case, each term is 1 over 3 times the previous term. That makes this a geometric series. So the geometric series and p-series can look very similar. You just check whether the summing index n is in the exponent or the base. If it's 1 over n cubed, where n is in the base of the exponential, then it's p-series. If you see a constant, if you see the base is a constant and the exponent contains n, then it's not a p-series. Okay. Now, of course, when you see a series, you ask the question, does it converge? Here is a simple rule to determine whether a p-series converges. The general p-series, the sum n from 1 to infinity of 1 over n to the p, this converges, converges when p is larger than 1. This diverges when 0 smaller than p, smaller than or equal to 1. Remember that when p equals 1, we get the harmonic series, which is the sum of 1 over n, and that's actually a series we talked about in the last lecture, and we proved that's not a convergent series, right? So here we generalize that statement, and we get the general result for the p-series, and we say the p-series converges if and only if p is larger than 1. Let's see a couple examples. First, the sum of 1 over n to 0.9. Now this series diverges. Why? Because it is a p-series with, let's write here, with p equals 0.9. And according to our rule, according to our test for convergence, when p is smaller than or equal to 1, the p-series diverges. Okay. And here, the classic harmonic series, which is one of the most important or commonly found series in mathematics. This is a divergent series. This diverges. Now we already proved the statement that the harmonic series diverges in the last lecture, but we can also claim it's divergent because it is a p-series with p equals 1. Okay, and the last one, the sum n from 1 to infinity, 1 over n to the, say, 1.1. So we're gradually increasing the exponent of the denominator from 0.9 to 1 to 1.1, and we end up with a convergent series. Here I'll present a proof of the test for convergence. We'll see why the series converges if and only if p is larger than 1. It's not a very complicated proof. It uses the geometric representation of integration. It's not a long proof, but I think it's a rather elegant proof. All right, let's check that out. Proof of test of convergence. Proof of, test of, let's call it p-series convergence. Let's just quickly go back to the test for convergence, the statement itself. So we want to prove that the p-series converges when p is larger than 1 and diverges when p is smaller than or equal to 1. To prove this, the strategy of the proof is to compare the p-series to certain integral. And that integral is going to be the integral of 1 over n. So let's look at the integral from 1 to infinity of 1 over n dn. Well, we consider n as a continuous variable. If you draw out the graph of 1 over n, it should look something like this. It's a curve that blows up, goes to infinity when n decreases to 0, and 1 over n goes to 0 as n go to infinity. Okay, and at 1 over n equals 1 when n is 1. So this is the point 1, 1. Let me just write 1 here. Now, this shaded area is the integral, right? Because an integral of a function gives you the area underneath that function, underneath the curve given by that function. So the integral of 1 over n from 1 to infinity gives you the area of this shaded region. Now, what is the summation of 1 over n to the p? Oh, sorry, I mean the integral of 1 over n to the p. Okay, my bad. Let me rewrite this. P is P is way too small. 1 over n to the p. Yep. Okay. So we're considering the integral of 1 over n to the p, not just 1 over n, but it doesn't change the really change the graph at all. Okay, now let's look at 1 over n to the p. Let's call this f of n equals 1 over n to the p. N to the p. Okay. Now let's look at the sum of 1 over n to the p. Well, the sum of 1 over n to the p can be can be written as 1 over 1 plus 1 over 2 to the p plus 1 over 3 to the p, or it can be graphically represented as the sum of these of the sum of the areas of these rectangles. Because if you look at the first rectangle, let's call that rectangle 1, rectangle 2, rectangle 3, rectangle 4. Area of the rectangle 1 is, now the base of the rectangle has length 1, so it's just 1, multiplied by the height of the rectangle, which is f of 1, which is 1 over 1 to the p, which is 1. So the area of the first rectangle is 1, and the area of the second rectangle rectangle 2 is, the base of the rectangle is, again, 3 minus 2 equals 1. The height of the rectangle is f of 2, which is 1 over 2 to the p. And the area of the third rectangle is 1 times f of 3, which is 1 over 3 to the p, so on and so forth. So we get that the area of each rectangle equals one term in the series. And if you sum them up, you get total area of rectangles equals the integral, not the integral, I mean equals the series, and from 1 to infinity of 1 over n to the p. Now, obviously, the area of the rectangles is larger than the area of the shaded region. So we get this statement, since the total area of rectangles equals is larger than or or equal to area of shaded region, you don't really need the equal to. You can write larger than because it's actually a strict inequality. But I'm just more used to writing larger than or equal to signs. Okay, we have. Sorry, let's just write strict inequalities to avoid the confusion. We have the statement that the sum one over n to the p is larger than the integral 1 to infinity of 1 over n to the p dn. This statement proves the second part of the test of convergence because 1 over p n to the p is not integrable. Is not integrable on 1 to infinity when p is between 0 and 1. Not integrable means like the integral of the integral of 1 over n to the p from 1 to infinity is infinity. We write the integral. I mean, you can write the integral equals infinity, but technically, in the mathematical term, it means it's not integrable. So we say something is integrable when the integral gives you a number, and infinity is not a number. It just means the integral blows up. Yeah, so so since the integral the integral of 1 over n to the p is infinity when p is between 0 and 1, and the sum of 1 over n to the p is even larger than that integral, we know that the series diverges when 0 is smaller than p, smaller than or equal to 1. Because I mean, if a smaller thing equals infinity, then the even larger thing must be infinity as well, and that means it diverges. All right, so that gives us the second part of the statement. Now let's see how we can obtain the first part, which is the series converges when p is larger than 1. We use a similar method. The only issue is let's go back to this diagram. The series is given by the rectangles, and we see that the rectangles are the areas of the rectangles is actually larger than the area of the shaded region. But it occurs to us, if we can remove one rectangle and fit the rest underneath the curve, then wouldn't that mean the series subtract the first term of the series is smaller than or equals is smaller than or equal to the integral? So to put it formally, what we mean is this. Let's consider the same diagram. F of n equals 1 over n to the p, and from 1 to infinity, the shaded region is once again the area. The area of the shaded region is once again the value of the integral. Now let's remove the first term of the series. So let me just repeat this. Area of shaded region equals the integral from 1 to infinity of 1 over n to the p dn. Okay, now let's remove the first rectangle and look at these rectangles instead. What I mean is you actually realize the first rectangle here is equivalent to the second rectangle in the previous diagram, and the second rectangle here is equivalent to the previous third rectangle. Now let's label them. Let's call this rectangle 1. Well, you can see that. So that's rectangle 1. That's rectangle 2. That's rectangle 3. If you look at the area of rectangle 1, you'll find it to be the base equals 1 and the height equals f of 2, which is 1 times 1 over 2 to the p. And area of rectangle 2 is 1 times f of 3, which is 1 over 3 to the p. And area of rectangle 3 is 1 times f of 4, which is 1 over 4 to the p, so on and so forth. If you sum the areas of the rectangles, you get the total area of rectangles equals 1 over 2 to the p plus 1 over 3 to the p plus 1 over 4 to the p plus dot dot dot, which is the sum n from 2 to infinity of 1 over n to the p. Note that this series differs from the original series by only the first term. So this is what I meant by removing the first rectangle or removing the first term. So we get the original series n equals 1 to infinity of 1 over n to the p equals the first term plus the remainder of the series equals 1 plus total area of rectangles. Since in this diagram, since we removed the first rectangle and fit all the remaining rectangles underneath the curve, we get that the total area of these rectangles is actually smaller than the area of the shaded region. So total area of rectangles is smaller than area of shaded region. Therefore, this sum from n from 2 to infinity of 1 over n to the p is smaller than the integral from 1 to infinity of 1 over n to the p dn. Right. And we can add 1 to each side, as we have the sum of the p series starting from n equals 1 is smaller than 1 plus the integral from 1 to infinity of 1 over n to the p dn. Now this is going to help us prove the first part because uh, 1 over n to the p is integrable on the interval from 1 to infinity when p is larger than 1. What this means is the integral from 1 to infinity 1 over n to the p dn is finite. Okay, since this is integrable since the function 1 over n to the p is integrable on 1 over 1 to infinity, that means the integral gives you a finite number, and if you add 1 to a finite number, you get another finite number, and then the infinite series of 1 over n to the p is smaller than a finite number, then the series gives you another finite number, which means the series converges. Converges when p is larger than 1. Okay, and that concludes the proof. So I think it's a very beautiful proof because we represent the integral and the infinite series with areas of rectangles and an area underneath a curve, and we compare these areas visually. Okay, let's move on. The next thing we're going to discuss is the ratio test. The ratio test is another method to determine the convergence and divergence of a given series. it's not a method specific to the p-series. It's a method that can be applied to any general series. So after this, after we learn this, we will have learned two general tests, which is the limit test in the last lecture, which can only determine the divergence of a given series, and then the ratio test we've learned we're about to learn, which has criterion that can be used to determine both convergence and divergence of a given series. And we also learned convergence tests that are specific to certain series. First, the geometric series, we learned that the geometric series is convergent only when the constant multiple is smaller than 1, the absolute value is smaller than 1, and then also the p-series convergence test that we just saw. So two general tests and two tests that are specific to series, geometric series and p-series. And after this, after the ratio test, we will learn a third general series test, which is called the comparison test. The name is kind of self-explanatory, so you just compare a series to a known series. So when you want to determine the convergence of certain series, you compare it to some other series to which you know the convergence of. That will be covered later. Now let's look at the ratio test. The statement of the ratio test is given as follows. Let me write this in red. Let the infinite series have infinite series have have non-zero terms. The only reason to this is that for the ratio test, essentially you're comparing the ratio between the terms. So you're dividing every term by the previous term. And if you get zeros, if you get just trivial series zeros everywhere, then because you have zero in the denominator, so you're in trouble. Here we're just excluding all the zeros and say this is a series with non-zero terms. So every single term is non-zero. Then the series converges if limit of n go to infinity of an plus 1 divided by an is smaller than 1, and the series diverges if this limit has absolute value larger than 1 and if the absolute value equals 1, it means the test is inconclusive. So it doesn't tell you anything. You have to use another method to determine the convergence. Next, let's go through two practice problems together. The first one is, we want to determine the convergence or divergence of the series m equals 0, infinity, 3 to the n divided by n factorial. Alright, so we want to apply the ratio test. Let's first write out the nth term in the series, which is 3 to the n divided by n factorial. And therefore, a n plus 1 equals 3 to the n plus 1 divided by n plus 1 factorial. Right, and then we have a n plus 1 divided by a n equals 3 to the n plus 1 over n plus 1 factorial divided by 3 to the n divided by n factorial. Clean it up a little bit. We get 3 to the n plus 1 times n factorial divided by 3 to the n times n plus 1 factorial. Now notice that n plus 1 factorial is n plus 1 times n factorial. And n factorial cancel out, so we get 3 to the n plus 1 divided by 3n times n plus 1. And divide top and bottom by 3 to the n, we get 3 over n plus 1. Therefore, the limit of n go to infinity of absolute value of a n plus 1 divided by a n equals the limit n go to infinity of 3 over n plus 1, which is 0. And since this is smaller than 1, we know that the series 3 to the n divided by n factorial converges. Okay, let's do another problem. Exercise 2. Again, determine the convergence or divergence convergence or divergence of the series given by n from 1 to infinity, n divided by 2 to the n. Once again, let's write out the term an, which is n divided by 2n. An plus 1 equals n plus 1 divided by 2 to the n plus 1. Therefore, we have an plus 1 divided by an equals n plus 1 over 2n plus 1. The denominator is n over 2n. Now simplify this, we get n plus 1 times 2 to the n divided by n times 2 to the n plus 1, which is n plus 1 over 2n. Take the limit, absolute value of an plus 1 divided by an. This is the limit as n go to infinity of absolute value of n plus 1 divided by 2n. Now this is obviously positive, so this is just the limit of n plus 1 over 2n. And this is 1 over 2 because the limit of n plus 1 divided by n is 1. Okay, and since this is, once again, smaller than 1, then we get the series converges. All right, the last convergence test I want to talk about today is the comparison test. For the comparing test, essentially, if you want to determine the convergence or divergence of a given series, say AN, you compare it to some other known series Bn. Say you know whether Bn converges or not, and you compare the series An to the series Bn, and judging by the convergence or divergence of Bn, you reach some sort of conclusion about the series in question An. The complete statement is this. Let yep, An and the sum of Bn be two infinite series with non-negative terms. So every single term is non-negative. Then if the infinite series n from 1 to infinity of Bn converges and An is between 0 and Bn. So An is non-negative, but also is smaller than or equal to Bn. Then the series An converges as well. And if the series Bn diverges, and this time An is larger than or equal to Bn, then the series An diverges. The statement is quite intuitive because if, say, Bn is an infinite series with non-negative term, then if it diverges, since it's non-negative, then the only possibility of it being divergent is that it goes to infinity. And if An, the series An, is even larger than Bn, then it also goes to infinity, right? And for the first statement, if Bn converges and if it's a non-negative series and it converges, then it means the terms have to be sufficiently small so that the summation of those is a finite number. And since An is even smaller than Bn, then the series summation of An grows even slower, so that series converges as well. So that's the intuitive understanding of the theorem. Obviously, from the statement of the theorem, we can see that if we want to determine the convergence or divergence of some series An, the key is to find an appropriate series Bn to compare it to. So let's go through two practice problems together to see how that's usually done. The first problem is to determine the convergence or divergence. I'm just going to abbreviate this as conv or div of the series equals 3 to infinity of 1 over n squared times ln of n. Okay, to determine the convergence or divergence of this, we need to find an appropriate series Bn to compare this to. Now we notice that when n is larger than or equal to 3, ln of n is larger than or equal to 1. is larger than or equal to 3, we have ln of n is larger than or equal to 1 because the exponential constant 2 is between 2 and 3. That means n squared times ln of n is larger than or equal to n squared when n is larger than or equal to 3. And immediately that tells us 1 over n squared times ln of n is smaller than or equal to 1 over n squared when n is larger than or equal to 3. Right, because a larger denominator gives you a smaller number. And obviously everything is positive here because n squares are never negative, and ln when n is larger than ln of n when n is larger than or equal to 1, it also gives you a positive number. So we get that everything is positive, and we found a series 1 over n squared that can bound our original series 1 over n squared times ln of n. And we know, this is a well-known fact, that the series 1 over n squared converges, since this is a p-series that we just talked about, right? This is a p-series with p equals 2. So that means, let me just write it down, because this is a p-series, with p equals 2. That tells us the series 1 over n squared converges. Then, by the ratio test, we know the sum of 1 over n squared times ln of n converges as well. Right, because we found a series, in this case, our series an is, the sum of an is the sum of 1 over n squared times ln of n, and our series bn is the sum of 1 over n squared. And since we know that the series bn 1 over n squared is convergent, and each term an is smaller than or equal to bn, then by the ratio test, the original series an, the sum of an converges as well. Okay, another example would be this series. Conv div of the series n from 2 to infinity 1 over square root of n squared minus 3. Alright, first of all, when n is larger than or equals 2, then everything is well defined because n squared will be larger than or equal to 4, so we don't get a negative number instead of square root, and neither do we get a 0 on the denominator, so everything is well defined. And well, we don't really know what square root of n squared minus 3 looks like, but we can, you can take a guess. Well, first, let me just tell you that the series Bn we are trying to find is 1 over n. The logic is this. N squared minus 3, when n is super large, then the 3 is almost negligible. So square root of n squared minus 3 behaves just like square root of n squared when n is super large. And square root of n squared is just n. So that's how we find the target series Bn. So we say that the series an and this original series an and the series bn defined by the sum of 1 over n is very similar. and we just make sure that Bn is, although similar to An, is slightly smaller. So here's the formal proof. What should I write? Right. Okay. Since maybe I should just write An and Bn just so that this looks cleaner. Let Bn equals, well, An equals 1 over square root of n squared minus 3. Bn equals 1 over n. Okay. Since n squared minus 3 is smaller than or equal to n squared, we have square root of n squared minus 3 is smaller than or equal to square root of n squared. And this is when n is larger than or equals 2. Now this is important because when n is smaller than 2, then the square root of n squared minus 3 is not well defined. But if it is well defined, then of course it works out because the stuff inside the square root is larger. Now once again, if you put this on the denominator, then a larger denominator means a smaller number. Therefore, 1 over square root of n squared minus 3 is smaller than or equal to 1 over square root of n squared, which equals 1 over n when, again, when n is larger than or equals 2. So that tells us An is smaller than or equal to, oh, sorry, I mean, this is larger than or equals to because a smaller denominator gives you a larger number. That means An is larger than or equal to Bn, and which obviously is larger than or equal to 0 because 1 over n is a positive number. This is when n is larger than or equals 2. And by the ratio test, we know before we use the ratio test, we have to find out whether the series Bn converges or not. We know the series Bn equals to infinity 1 over n. Diverges. This is just a harmonic series starting from the second term. And we know that the harmonic series diverges. Now, if you exclude one term, it makes no difference at all. Because when you're talking about divergence and convergence, you really care about the infinitely many terms that follow. Taking away the first or second or third term doesn't really make a difference. Okay, so we know that this series diverges, and then by the ratio test, the series from 2 to infinity, an, which is 2 to infinity, 1 over n squared minus 3 diverges as well. Okay, so this is the comparison test. And now just a quick summary. We've learned 5 tests so far, 3 general tests that can be applied to any series. That's the comparison test, the limit test that we learned in the last lecture, and the what's the third one? All right, and the ratio test. So we have the comparison test, the ratio test. These are the two. Oh, that's why I don't know what I'm writing. This is the comparison test. Hang on, sorry. Did I write this wrong as well here? Yeah. Sorry about that. So as I was saying, we have three general tests that can be applied to any series. That's the comparison test and ratio test we learned today, and the limit test in the last lecture. And we also have two convergence tests that are for geometric series and P series, respectively. All right, so 5 tests in general. All right, that's all for today. I'll see you all on Friday.